The Banqiao Dam was constructed between 1951 and 1952 on the Ru River, a tributary of the Huai River system in Henan Province, central China. The dam was part of a comprehensive flood control and irrigation program initiated following catastrophic flooding of the Huai River in 1950, which caused widespread destruction across the Central Plains. The program was announced in April 1957 as part of the state's campaign to harness the Huai River, a policy directive that sought to transform the region's hydrology through the construction of reservoirs, embankments, and diversion structures. The Banqiao Dam was designed as an earth core embankment structure, with initial specifications calling for a height of 21.5 meters and a storage capacity of 244 million cubic meters. The design philosophy reflected Soviet engineering practices prevalent in China during the early 1950s, emphasizing rapid construction, mass mobilization of labor, and the prioritization of water accumulation for irrigation over conservative safety margins in spillway design. The design of the Banqiao Dam assumed a specific hydrological regime. Engineers calculated the design flood using available rainfall records from the region, which at that time covered a limited historical period. The design flood was set to correspond to a once-in-1,000-year return period event. This return period was not derived from a millennium of observational data, but from statistical extrapolation of a much shorter dataset, combined with theoretical probability distributions. The design assumed that extreme rainfall events would conform to predictable statistical patterns and that the regional climate was stationary, that is, that future extreme events would resemble past extremes in both magnitude and frequency. Under this assumption, the spillway was sized to pass a peak inflow of 1,742 cubic meters per second, which was calculated as the maximum discharge expected once every 1,000 years. The spillway consisted of 5 sluice gates, each designed to release water under gravity when manually opened by operators. The gates were not automated. The design assumed that operators would have sufficient advance warning of extreme rainfall events and that they would have the authority and capability to open the gates in time to prevent overtopping. The reservoir's primary function was to store water for irrigation during dry seasons and to attenuate flood peaks during wet seasons. The dam was intended to protect downstream areas, including agricultural land and small towns, from seasonal flooding. The design also incorporated a secondary benefit, the potential for small-scale hydroelectric generation, though this function was not prioritized in the initial construction phase. The dam's embankment was constructed using locally sourced clay and soil, compacted in layers. The core of the dam was designed to be impermeable, preventing seepage through the body of the structure. The downstream slope was protected by riprap to prevent erosion from wave action and overflow. The upstream slope was designed to withstand the hydrostatic pressure exerted by the full reservoir. The foundation was prepared by clearing vegetation and loose soil, then compacting the natural ground to provide a stable base for the embankment. The design assumed that the foundation would remain stable under the combined loads of the embankment weight and the water pressure from the full reservoir. During the initial filling of the reservoir in 1953, structural problems emerged. Cracks appeared in the embankment, and observers noted localized subsidence in sections of the dam crest. Investigation revealed that construction quality had been inconsistent. Compaction of the embankment layers had not been uniform, and in some areas the specified moisture content for optimal compaction had not been achieved. Additionally, the excavation of the foundation had not reached the required depth in certain zones, leaving pockets of loose or organic material beneath the embankment. These deficiencies were attributed to the pace of construction, which had prioritized meeting deadlines over adherence to engineering specifications. The use of mass labor unskilled workers mobilized from surrounding communes meant that supervisory control over construction quality was limited. When the cracks appeared, the decision was made to reinforce the structure. However, rather than excavating and rebuilding the deficient sections, engineers opted to raise the height of the dam and add an additional layer of compacted material over the existing embankment. This intervention increased the dam height to 24.5 meters and expanded the storage capacity to 492 million cubic meters. The modification introduced new assumptions into the system. The original design had been predicated on a specific reservoir volume and a corresponding hydrological balance between inflow, storage, and discharge. By doubling the storage capacity, the modification altered the relationship between reservoir volume and spillway discharge capacity. The spillway, which had been sized for the original reservoir configuration, was now expected to serve a reservoir with significantly greater storage potential. However, the spillway discharge capacity was not increased proportionally. The design modification assumed that the larger reservoir would provide greater flood attenuation capacity, allowing the spillway to handle peak inflows by temporarily storing excess water and releasing it gradually. This assumption was reasonable under the original hydrological parameters, that is, under the assumption that extreme inflows would conform to the design flood of 1,742 cubic meters per second. The modification did not anticipate inflows that would exceed the design flood by an order of magnitude. In 1961, further modifications were made to the dam. The number of spillway gates was reduced from 12 to 5 under the rationale of primacy to accumulation and irrigation. This reduction was consistent with the broader policy emphasis on maximizing water storage for agricultural use, rather than prioritizing flood discharge capacity. The decision reflected an institutional preference for water retention over flood control. The reduction in spillway gates decreased the total discharge capacity from 1,742 cubic meters per second to approximately 800 cubic meters per second under normal operating conditions. This reduction was not accompanied by a reassessment of the design flood or the return period used to calculate spillway adequacy. The assumption remained that extreme inflows would not exceed the original design flood, and that the larger reservoir volume would compensate for the reduced discharge capacity by providing additional temporary storage. The instrumentation at Banqiao Dam was minimal. Water level was monitored using staff gauges located at the upstream face of the dam and at key points within the reservoir. These gauges provided a visual indication of reservoir elevation, which operators could observe directly or report via telephone to the Central Management Office. There was no automated water level monitoring system. Inflow to the reservoir was not directly measured. Instead, inflow was estimated based on rainfall data collected from a small number of meteorological stations in the upstream basin. These stations provided daily rainfall totals, which were used to estimate runoff using empirical coefficients. The coefficients were derived from historical relationships between rainfall and observed stream flow, but these relationships had not been validated for extreme rainfall events. The system assumed that the relationship between rainfall and runoff would remain linear even under extreme conditions, an assumption that did not account for the nonlinear response of saturated catchments during prolonged, high-intensity rainfall. The spillway gates were manually operated. Each gate consisted of a vertical lift mechanism controlled by a hand-cranked winch. The winch required multiple operators to turn, and the time required to fully open a single gate was approximately 30 minutes under ideal conditions. The design assumed that operators would have sufficient time to open the gates in response to rising water levels, and that the gates would function as intended when called upon. There was no redundancy in the gate operating system. If a gate became obstructed or jammed, there was no alternative mechanism to release water through that gate. The design did not incorporate automated or emergency spillway systems that would activate independently of operator action. The organizational structure responsible for dam operations was hierarchical. Local operators at the dam site reported to a Regional Water Resources Bureau, which in turn reported to the Provincial Water Resources Department. Decision-making authority for major operational actions, such as opening spillway gates during flood events, rested with the Regional Bureau, not with on-site operators. This structure assumed that the Regional Bureau would have access to timely and accurate information about reservoir conditions and meteorological forecasts, and that communication links between the dam site and the Bureau would remain functional during extreme events. The structure also assumed that the Regional Bureau would prioritize dam safety over other considerations, such as downstream water supply or political directives to maintain high reservoir levels for irrigation. The training provided to dam operators emphasized routine maintenance and monitoring. Operators were instructed to observe water levels, inspect the embankment for signs of seepage or cracking, and report anomalies to the Regional Bureau. training did not include scenario-based exercises for extreme flood events or decision-making under uncertainty. Operators were not trained to estimate inflow rates based on visual observation of reservoir behavior, nor were they trained to independently assess whether spillway discharge capacity was sufficient to prevent overtopping. The training assumed that extreme events would be managed by the regional bureau based on meteorological forecasts and that operators would follow instructions provided by higher authorities. The region's hydrological characteristics were understood in general terms but not in detail. The Ru River Basin was known to experience seasonal flooding, particularly during the summer monsoon season when warm, moist air from the Pacific Ocean brought heavy rainfall to central China. However, the historical record of extreme rainfall events in the region was sparse. The design flood calculation was based on rainfall data covering approximately 30 years, a period considered adequate for standard hydrological design, but insufficient to capture the full range of natural variability in the climate system. The design did not account for the possibility of tropical cyclones penetrating inland and stalling over the region, a phenomenon that had not been observed in the available historical record but that was physically plausible given the region's location relative to the Pacific Ocean and the topography of the surrounding mountain ranges. The Banqiao Dam, as constructed and modified, embodied a set of interlocking assumptions. It assumed that extreme rainfall would conform to statistical predictions derived from limited data. It assumed that spillway capacity, reduced to prioritize water storage, would be adequate because extreme inflows would be rare and would not exceed design parameters by significant margins. It assumed that operators would have advance warning, functional communication, and the authority to act. It assumed that the embankment, despite early structural issues, had been adequately reinforced and would perform as intended under maximum loading. It assumed that the foundation, despite incomplete excavation in some areas, would remain stable. It assumed that the gates, despite being manually operated and vulnerable to obstruction, would function when needed. Each assumption, considered individually, was defensible based on the engineering knowledge and institutional priorities of the time. Collectively, however, these assumptions created a system in which the probability of failure under conditions that exceeded design parameters was not merely possible, it was structural. The system was designed to function correctly under expected conditions, but it lacked the capacity to adapt or degrade gracefully under conditions that fell outside the boundaries of those expectations. The design had defined certain scenarios as implausible, and in doing so, it had rendered the system incapable of responding to those scenarios when they occurred. The vulnerabilities present in the Banqiao Dam system before August 1975 were not the result of sudden decisions or isolated errors. They were latent conditions, structural weaknesses embedded in design choices, organizational culture, maintenance practices, and operational procedures that had existed for years, waiting for the right combination of triggering events to activate them. Understanding these latent conditions requires examining not only what was present at the dam site, but also the broader institutional and political context within which the dam operated, the human factors that shaped operator behavior and decision-making, and the specific ways in which the control interface, the instruments, procedures, and communication systems, created predictable traps for operators attempting to manage an evolving crisis. The first latent condition was the incomplete characterization of hydrological risk. The design flood for Banqiao Dam, calculated as a once-in-1,000-year event with a peak inflow of 1,742 cubic meters per second, was derived from rainfall records covering approximately 3 decades. Statistical hydrology relies on the assumption that the sample period is representative of the full population of possible events. For the Ru River Basin, this assumption was questionable. The basin's location placed it at the intersection of several meteorological systems, the East Asian monsoon, which brought seasonal rainfall from the Pacific, continental air masses from the north and west, and less frequently, tropical cyclones that could penetrate inland after making landfall along the coast. The interaction of these systems could produce extreme rainfall events that were not well represented in the short historical record. The design did not incorporate paleoclimatic evidence, such as sediment records or historical flood accounts predating the instrumental record, that might have provided insight into the occurrence of extreme events over longer timescales. The design treated the calculated 1,000-year flood as a firm upper bound rather than as a probabilistic estimate with significant uncertainty. This treatment reflected a broader tendency in mid-20th century dam engineering to seek deterministic answers to inherently probabilistic questions. The second latent condition was the reduction in spillway capacity without corresponding adjustment of operational rules or safety margins. When the number of sluice gates was reduced from 12 to 5 in 1961, the total discharge capacity under full gate opening dropped from approximately 1,742 cubic meters per second to roughly 800 cubic meters per second. This reduction was justified on the grounds that the enlarged reservoir, now with a capacity of 492 million cubic meters, could temporarily store excess inflow during flood events, allowing operators to release water gradually rather than all at once. The logic was plausible under normal flood conditions. However, it introduced a critical vulnerability. If inflow exceeded the reduced discharge capacity for a prolonged period, the reservoir would fill faster than it could be emptied, and the only means of preventing overtopping would be to increase the number of gates or to open gates preemptively before the reservoir reached capacity. The operational procedures in place in 1975 did not include protocols for preemptive gate opening based on meteorological forecasts. Instead, procedures emphasized maintaining high reservoir levels to maximize water availability for irrigation during the dry season. Operators were instructed to keep the reservoir as full as possible and to release water only when levels approached the maximum design elevation. This procedure was rational from an irrigation management perspective, but it eliminated the buffer capacity that might have allowed the dam to absorb a sudden, extreme inflow event. The third latent condition was sedimentation in the spillway channels. Over the years of operation, sediment carried by inflowing water had accumulated in the reservoir, and critically, in the approach channels leading to the spillway gates. Sediment deposition was a known issue in reservoirs throughout the Huai River system. The upstream catchment had been subject to deforestation and agricultural intensification, both of which increased soil erosion and sediment delivery to rivers. The design of Banqiao Dam included provisions for sediment management, but these provisions were based on estimated sediment yield rates that proved to be lower than actual rates. By the mid-1970s, sediment had reduced the effective cross-sectional area of the spillway channels, meaning that even if all 5 gates were fully opened, the actual discharge capacity would be less than the design value of 800 cubic meters per second. The exact reduction in capacity was not quantified through field measurements. Operators were aware that sediment had accumulated, but there was no formal assessment of how much this accumulation had degraded spillway performance. The absence of this assessment meant that operational decisions were based on an assumed discharge capacity that no longer corresponded to physical reality. The fourth latent condition was the absence of independent verification and quality control during the dam's construction and modification phases. The initial construction in 1951 to 1952 had been carried out rapidly using mass labor mobilized from local communes. Supervision was limited, and construction techniques were inconsistent. When cracks appeared during first filling in 1953, the response was to raise the dam rather than to excavate and rebuild the deficient sections. This decision reflected both technical and political considerations. Technically, raising the dam was faster and required less disruption to ongoing operations. Politically, admitting that the dam had been poorly constructed would have been inconsistent with the narrative of success that accompanied large-scale infrastructure projects during this period. The modification work in 1955 to 1956, which raised the dam to 24.5 meters and increased storage capacity, was also carried out without independent engineering review. Soviet advisors had been involved in the initial design, but by the mid-1950s, political tensions between China and the Soviet Union had reduced technical cooperation. Chinese engineers were expected to proceed independently, but the institutional mechanisms for peer review, third-party assessment, and challenge of design assumptions were weak or non-existent. Engineers who identified potential problems faced pressure to align with official narratives of progress and success. This pressure created an environment in which raising concerns about dam safety could be interpreted as political dissent. The fifth latent condition was the alarm and communication system's inadequacy under extreme conditions. The dam was equipped with a basic telephone system linking the dam site to the Regional Water Resources Bureau and to a small number of meteorological stations in the upstream basin. The system relied on above-ground telephone lines, which were vulnerable to damage from high winds and heavy rainfall. There was no radio backup. During normal operations, this communication system was sufficient. Operators could report water levels daily, and the Bureau could provide routine instructions. However, the system was not designed to function during a severe storm. If telephone lines were damaged, the dam site would be isolated, and operators would have no means of receiving updated meteorological information or instructions from higher authorities. The design assumed that communication would remain intact during emergencies, an assumption that did not account for the correlated failure modes introduced by extreme weather. Additionally, the dam had no automated alarm system to alert downstream populations in the event of impending failure. Warning protocols relied on manual notification via telephone, which assumed both functional communication links and sufficient lead time to disseminate warnings. The absence of redundancy and automation in the communication and alarm systems meant that the system could fail precisely when it was needed most. The sixth latent condition was the training and mental model mismatch between operators and the physical system. Operators at Banqiao Dam were trained to manage the dam during normal and moderately high water conditions. They understood that the reservoir should be kept as full as possible to serve irrigation needs and that water should be released gradually to avoid disrupting downstream water supply. This mental model prioritized gradual controlled releases and avoided rapid drawdowns. The model was appropriate for managing seasonal variability in inflow, but not for managing a sudden extreme flood. Operators had no training in estimating inflow rates from visual observation of reservoir rise rates, no training in calculating time to overtopping under different inflow scenarios, and no training in making independent decisions under communication failure. Their mental model did not include the concept of sacrificing storage to preserve structural integrity. That is, the idea that it might be necessary to release water rapidly even if doing so reduced the reservoir's irrigation capacity in order to prevent the water level from reaching the crest. This mental model was reinforced by the procedural emphasis on maintaining high reservoir levels and by the institutional culture that discouraged independent action by lower-level operators. The seventh latent condition was the absence of a formal emergency action plan. In 1975, there was no documented plan specifying what actions operators should take in the event of an approaching extreme flood. There was no predefined threshold at which spillway gates should be opened, no protocol for preemptive releases based on meteorological forecasts, and no decision tree to guide operators if communication with the regional bureau was lost. The absence of such a plan reflected the broader assumption that extreme events were unlikely and that, if they did occur, they would be managed on an ad hoc basis by higher authorities. This assumption placed the burden of decision-making on the regional bureau, which was located several hours away from the dam site and which lacked real-time visibility into reservoir conditions. The Bureau's decisions would necessarily be based on delayed information, and any instructions issued to operators would reflect the situation as it had existed hours earlier, not as it existed at the moment the instructions were received. The eighth latent condition was the political and institutional context of the mid-1970s. By 1975, China was emerging from the Cultural Revolution, a period of intense political upheaval that had disrupted technical institutions, persecuted engineers and intellectuals, and prioritized ideological conformity over technical expertise. Many experienced engineers had been sidelined or purged. Decision-making authority had been concentrated in political cadres who lacked technical training. The institutional memory of the dam's design and construction had been fragmented. Chen Xing, a hydrologist who had opposed the policy of primacy to accumulation and irrigation and who had advocated for larger spillways and more conservative design margins, had been labeled a right-wing opportunist and removed from his position in the late 1950s. His warnings about the inadequacy of spillway capacity had been dismissed as excessively conservative and politically motivated. By 1975, The institutional culture had shifted somewhat. Technical expertise was beginning to be rehabilitated, but the structural features that had enabled the dismissal of technical warnings remained in place. There was still no mechanism for independent technical review, no protection for engineers who challenged official assumptions, and no institutional memory of the specific vulnerabilities that had been built into the Banqiao Dam. The ninth latent condition was the lack of monitoring and instrumentation for detecting embankment distress. The dam was equipped with staff gauges for water level and visual inspection protocols for detecting cracks or seepage, but it had no piezometers to measure pore pressure within the embankment, no settlement markers to detect deformation, and no seepage weirs to quantify seepage flow rates. These instruments, which were standard in many large dams by the 1970s, would have provided early warning of internal erosion, foundation instability, or other failure modes that could develop during prolonged high water levels. The absence of these instruments meant that operators had no way to assess the internal state of the dam. They could see the water level rising, but they could not know whether the embankment was developing internal weaknesses that might lead to sudden failure even before overtopping occurred. The design assumed that visual inspection would be sufficient, a reasonable assumption for detecting gross external anomalies, but inadequate for detecting subsurface processes that could compromise structural integrity. The 10th latent condition was the cascade potential within the basin. Upstream of Banqiao Dam were dozens of smaller dams and reservoirs, also constructed as part of the Harness the Huai River campaign. Many of these structures were even less robustly designed than Banqiao. Some were earthen dams with no spillways at all, relying entirely on controlled releases through outlet works. Some had been built by local communes without formal engineering design. The cascade potential, the possibility that failure of an upstream dam would send a surge of water downstream overwhelming the next dam in the sequence, was not formally analyzed during the design phase. The system-level assumption was that each dam would manage its own local inflow, and that coordinated releases could be managed through centralized planning by the regional bureau. This assumption did not account for the possibility that multiple dams might reach capacity simultaneously during a regional extreme rainfall event, or that communication failures might prevent coordinated action. These latent conditions did not exist in isolation. They were interdependent. The inadequacy of the spillway was compounded by the sedimentation that reduced discharge capacity. The absence of instrumentation was compounded by the lack of training in interpreting visual observations. The centralized decision-making structure was compounded by the communication system's vulnerability. The political culture that discouraged dissent was compounded by the absence of formal review mechanisms. Each latent condition reduced the system's resilience, its ability to absorb disturbances, adapt to unexpected conditions, and recover from partial failures without cascading into total collapse. The system, as it existed in August 1975, was brittle. It could function adequately under conditions that fell within the envelope of assumptions built into its design. But it had no margin for error, no redundancy, and no capacity for graceful degradation. When conditions exceeded the design envelope, the system would not bend, it would break. The human factors traps embedded in this system were predictable consequences of the design and organizational structure. Operators were placed in a role where they were responsible for monitoring the dam, but lacked the authority, training, information, and tools necessary to manage an extreme event. They were expected to follow procedures that prioritized irrigation over flood control. They were expected to defer to higher authorities for major decisions, but those authorities were remote and lacked real-time situational awareness. They were expected to trust that the spillway, if fully opened, would be adequate to prevent overtopping, but they had no independent means of verifying this assumption. The system had been designed to create the illusion of control. Staff gauges provided precise water level readings, procedure-specified actions, and the hierarchical structure defined clear lines of authority, but the control was superficial. The operators could see the water rising, but they could not make it stop rising fast enough. They could open the gates, but the gates could not discharge water fast enough if the gates were obstructed or if inflow exceeded the reduced capacity. They could report conditions to the Bureau, but only if the telephone lines remained intact. The trap was this: the system had been designed to make operators believe that following procedures and trusting the design would ensure safety. The procedures and the design were predicated on assumptions that had never been validated under extreme conditions. When those assumptions were violated, the procedures would not work, and the design would fail, but operators would have no way of knowing this until the failure was already underway. The system did not provide operators with the information they needed to recognize that they were in uncharted territory. It provided them with the information they expected to see: rising water levels, gates opening, without indicating that these actions were insufficient. The latent conditions guaranteed that when the extreme event arrived, the system would guide operators down a path that felt correct, looked correct, and was procedurally correct, but that would nonetheless lead to failure. The sequence of events that initiated the failure of Banqiao Dam began not at the dam itself, but hundreds of kilometers to the southeast, over the Pacific Ocean, where atmospheric conditions in late July 1975 gave rise to a tropical disturbance that would become Typhoon Nina. On July 29, 1975, meteorological stations in the Philippine Sea detected the formation of a tropical depression. Over the following days, the system intensified as it moved northwestward, drawing energy from warm ocean waters. By August 1st, the system had been classified as a typhoon and assigned the designation Nina, the third major tropical cyclone of the 1975 Western Pacific typhoon season. Typhoon Nina made landfall on the coast of Fujian Province on August 3, 1975, as a strong typhoon with sustained winds estimated at 160 kilometers per hour. Under normal circumstances, a typhoon making landfall would rapidly weaken as it moved inland, cut off from the ocean moisture that fueled its circulation. Typhoon Nina did not follow this pattern. After making landfall, Nina encountered an unusual atmospheric configuration. A strong high-pressure system had established itself over the Yellow Sea to the northeast, blocking Nina's typical recurvature path toward Japan. Simultaneously, a trough of low pressure extended from the west, creating a steering flow that guided the typhoon inland, rather than allowing it to dissipate or veer back toward the ocean. This configuration caused Nina to stall over the provinces of Fujian, Jiangxi, and Hunan for several days, during which the storm's circulation continued to draw moisture from the ocean and transport it inland. The result was sustained, intense rainfall over a broad region of central China. By August 4th, the storm had begun to move northward into Henan Province directly toward the Huai River Basin. Meteorological observations from stations in Henan Province recorded the arrival of heavy rainfall on the evening of August 4. Initial rainfall rates were moderate, approximately 10 to 20 millimeters per hour, but as the typhoon's circulation became fully established over the region, rainfall intensified. By the morning of August 5, rainfall rates in some areas of the upper Ru River Basin exceeded 100 millimeters per hour. This rate of rainfall was extraordinary. The design rainfall for Banqiao Dam, used to calculate the design flood, assumed a maximum 24-hour rainfall total of approximately 400 millimeters. Between August 4 and August 8, cumulative rainfall in the upper Ru River Basin exceeded 1,600 millimeters, 4 times the design value. The peak 24-hour rainfall total, recorded at a station near the town of Linzhuang, was 1,060 millimeters, more than 2.5 times the design value. This was not merely an exceedance of the design flood, it was an exceedance by an order of magnitude that invalidated the fundamental assumptions underlying the spillway design. The Banqiao Reservoir began to rise rapidly on the evening of August 5. At 8 p.m. local time, the water level stood at 105.5 meters above sea level, approximately 2.5 meters below the normal maximum operating level of 108 meters. Operators on duty at the dam observed the rising water and, following standard procedure, reported the level to the Regional Water Resources Bureau via telephone. The Bureau's response, based on the information available at that time, was to authorize limited gate openings to begin releasing water. The operators opened 2 of the 5 sluice gates, partially approximately 1/4 of full opening, initiating a discharge of approximately 160 cubic meters per second. This discharge rate was consistent with normal flood management procedures, which called for gradual releases to avoid disrupting downstream water supply and to preserve as much storage capacity as possible for continued irrigation use. However, the inflow to the reservoir during this period was not being directly measured, There were no streamflow gauges on the Rue River upstream of the reservoir that could provide real-time inflow data. Instead, operators and bureau staff relied on rainfall reports from meteorological stations and on visual observation of the rate at which the reservoir level was rising. Based on the initial rate of rise, operators estimated that inflow was approximately 300 to 400 cubic meters per second higher than normal, but not extraordinary. This estimate was reasonable based on the information available, but it was incorrect. The actual inflow rate at this time was significantly higher, likely exceeding 1,000 cubic meters per second, because the catchment upstream of the reservoir was already saturated from earlier rainfall, and the runoff coefficient, the fraction of rainfall that becomes streamflow, had increased from its normal value of 0.3 to 0.4% toward a value approaching 0.7% or higher. The operators had no way of knowing this. Their mental model of catchment response was calibrated to normal conditions, where rainfall converted to runoff gradually and where there was a lag of several hours between peak rainfall and peak inflow. Under the saturated conditions produced by multiple days of heavy rainfall, this lag had collapsed, and rainfall was converting almost immediately to runoff. By midnight on August 5th, the water level had risen to 106.8 meters, more than 1 meter in 4 hours. The rate of rise was accelerating. Operators opened the remaining 3 sluice gates, bringing all 5 gates to partial opening, increasing total discharge to approximately 400 cubic meters per second. This action was consistent with procedure and with the operators' understanding of the situation. They believed that by opening all available gates they were discharging water at the maximum feasible rate, and that this discharge, combined with the large storage capacity of the reservoir, would be sufficient to prevent the water level from reaching the crest elevation of 110.5 meters. This belief was based on 2 assumptions. First, that the spillway gates, when fully opened, could discharge approximately 800 cubic meters per second as designed, and second, that inflow would peak and then decline as the storm moved away from the basin. Both assumptions were incorrect. The first assumption failed because of the sedimentation in the spillway channels. When operators attempted to open the gates fully during the early morning hours of August 6, they discovered that 2 of the 5 gates could not be opened beyond approximately 60% of full opening. The gates were physically obstructed by accumulated sediment and debris in the approach channels. The operators reported this obstruction to the regional bureau via telephone, but there was no immediate remedy. Clearing the obstructions would have required sending work crews into the spillway channels during the storm, an action that was both dangerous and logistically infeasible given the conditions. The effective discharge capacity of the spillway, which should have been 800 cubic meters per second with all gates fully open, was reduced to approximately 600 cubic meters per second and possibly lower, because even the gates that could be opened were discharging less than their designed capacity due to the reduced cross-sectional area of the channels. The operators did not know the exact discharge rate. They knew only that the gates were open and that water was flowing through them. The second assumption, that inflow would peak and decline, failed because the storm did not move away. Typhoon Nina stalled over the Huai River basin. Rainfall continued at high intensity throughout August 6 and into August 7. The inflow to Banqiao Reservoir, rather than peaking and declining, remained at extreme levels for more than 48 hours. By the afternoon of August 6, the water level had reached 107.9 meters, just 0.1 meters below the normal maximum operating level. The rate of rise had slowed somewhat due to the spillway discharges, but it had not stopped. The reservoir was gaining water faster than it was losing it. The operators could see this from the staff gauges, but they had no tools to calculate how long it would take for the reservoir to reach the crest or what inflow rate would be required to stabilize the water level at its current elevation. Their understanding of the situation was qualitative, not quantitative. They knew the situation was serious, but they did not know whether it was manageable or whether failure was already inevitable. At this point, approximately 3 p.m. on August 6, the telephone lines connecting the dam to the regional bureau failed. The lines had been damaged by high winds and falling trees. The dam site was now isolated. Operators could no longer receive instructions from higher authorities, and they could no longer report updated conditions. The loss of communication meant that decision-making authority by default fell to the operators on site. However, The operators had no training or procedures for this scenario. They were expected to follow instructions from the Bureau, not to make independent decisions about major operational actions. The mental model that guided their actions was still oriented toward following procedure and waiting for guidance. In the absence of communication, they continued to do what they had been doing, maintaining the gates in their current positions and monitoring the water level. The water level continued to rise. By 8 p.m. on August 6th, it had reached 108.3 meters, exceeding the normal maximum operating level. At this elevation, the reservoir volume was approximately 500 million cubic meters, near the designed maximum storage capacity. The freeboard, the vertical distance between the water surface and the crest, was now 2.2 meters. Under normal design assumptions, this freeboard provided a safety margin against wave action and short-term inflow surges. However, the current situation was not a short-term surge. It was a sustained extreme inflow event. The reservoir was continuing to fill, and there was no longer any storage capacity available to attenuate inflow. Every cubic meter of water entering the reservoir in excess of spillway discharge was raising the water level. The operators, observing the continued rise, recognized that the dam was in danger. They attempted to send a messenger by bicycle to the nearest town with a functioning telephone, approximately 15 kilometers away, to request emergency assistance. The messenger departed at approximately 9 p.m. on August 6, but did not reach the town until after midnight due to flooded roads and washed-out bridges. When the message finally reached the regional bureau in the early hours of August 7th, the bureau's response was to authorize the operators to take any actions necessary to prevent overtopping, including the possibility of attempting to breach sections of the embankment in controlled locations to release water laterally. However, this authorization did not reach the operators at the dam because the telephone lines remained down and there was no alternative communication method. During the night of August 6 to August 7, the situation at the dam deteriorated rapidly. The water level rose past 109 meters, then past 109.5 meters. Freeboard was now less than 1 meter. Wave action driven by high winds was beginning to wash over the crest in isolated locations. Operators and local residents who had gathered at the dam attempted to reinforce the crest by piling sandbags and earth along the top of the embankment, creating a temporary extension to increase the effective crest height. This work was carried out in darkness, in heavy rain, with limited tools and materials. The reinforcement raised the effective crest elevation by approximately 0.5 meters in some sections, but the work was uneven and the materials were not compacted. The reinforcement was a desperate measure, improvised under emergency conditions, with no expectation that it would withstand sustained overtopping. At approximately 1 a.m. on August 7, the water level reached 110 meters, just 0.5 meters below the original crest elevation, and within the zone of the improvised reinforcement. The rate of rise was still approximately 0.3 meters per hour, implying that the crest would be reached within 2 hours unless inflow decreased or spillway discharge increased. Neither occurred. The storm continued. The gates remained in their obstructed positions, discharging approximately 600 cubic meters per second. The inflow, estimated from the rate of rise and the reservoir's surface area, was approximately 1,500 to 2,000 cubic meters per second. The imbalance in flow exceeding discharge by 900 to 1,400 cubic meters per second was driving the reservoir relentlessly toward overtopping. At 1:30 a.m. on August 7th, the first sustained overtopping began. Water began to flow over the improvised crest reinforcement in a section near the center of the dam. The flow was initially shallow, less than 0.1 meters deep, and the velocity was low. However, the flow began to erode the loose earth and sandbags that formed the reinforcement. Within minutes, the reinforcement in that section had been washed away, and water was flowing over the original crest. The erosion process accelerated. Water flowing over the crest began to scour the downstream face of the embankment. The embankment material, compacted clay and soil, was not designed to resist the erosive forces of flowing water. The downstream slope began to slump and collapse. As material was removed, the effective crest elevation lowered, allowing more water to flow over, which removed more material, further lowering the crest. This positive feedback loop overtopping leading to erosion leading to increased overtopping initiated the breach formation process. By 2 a.m., the breach had widened to approximately 10 meters and deepened by approximately 1 meter. Water was now pouring through the breach at high velocity, estimated at 5 to 7 meters per second. The discharge through the breach was far greater than the discharge through the spillway gates. The operators, observing the breach formation, recognized that the dam was failing and that there was no action they could take to stop it. They evacuated the dam crest and moved to higher ground. There was no means to warn downstream populations. The alarm system relied on telephone communication, which was not functional. Some operators attempted to physically travel to nearby villages to warn residents, but the roads were flooded and travel was extremely difficult. Most downstream residents had no warning that the dam was failing. The breach continued to grow throughout the early morning hours of August 7th. By 3 a.m., the breach width had reached approximately 50 meters, and the breach depth had cut through the full height of the embankment down to the foundation level. The discharge through the breach peaked at an estimated 78,100 cubic meters per second, more than 90 times the designed spillway discharge capacity. The reservoir, which had held approximately 600 million cubic meters of water at the moment overtopping began, drained approximately 500 million cubic meters through the breach over the following 5 hours. The discharge formed a flood wave that propagated downstream at an average velocity of approximately 50 kilometers per hour, reaching the towns of Sweeping and Daowensheng within 1 hour of breach formation. The physical mechanism of the breach can be reconstructed from the observed behavior and from post-failure analysis of the breach geometry. The initial overtopping eroded the downstream slope, creating a headcut, a vertical or near-vertical face in the embankment material. The headcut migrated upstream toward the crest as flowing water undercut the material at the base of the headcut, causing the material above to collapse. When the headcut reached the crest elevation effectively lowered, increasing the depth of flow over the breach, which increased the erosive force. The breach widened laterally as erosion undercut the sides of the breach, causing material to slump into the flow. The embankment material did not have sufficient cohesive strength to resist the shear forces imposed by the high-velocity flow. The foundation beneath the embankment, consisting of natural soil and rock, was also eroded as the breach cut downward, though at a slower rate than the embankment material itself. The breach process continued until the water level in the reservoir had dropped to the elevation of the foundation at the breach location, at which point the driving head for flow through the breach was reduced and the erosion rate decreased. The failure was not instantaneous. It was a progressive process that took approximately 5 hours from initial overtopping to full breach development. During this time, the operators at the dam could observe the process unfolding but could do nothing to stop it. Their mental model of the situation, that opening the spillway gates would prevent overtopping, had been invalidated by the extreme inflow, the obstructed gates, and the sustained duration of the storm. They had followed procedures. They had reported conditions to higher authorities when communication was available. They had improvised reinforcements when it became clear that overtopping was imminent. None of these actions were sufficient. The system had been designed under assumptions that were no longer valid, and when those assumptions failed, the system had no capacity to adapt. Upstream of Banqiao Dam, the extreme rainfall was causing similar problems at dozens of smaller dams. Many of these structures were experiencing inflows that exceeded their spillway capacities. Communication between dams was disrupted by the storm. There was no coordinated basin-wide management of releases. As water levels rose at these upstream dams, some began to fail. The first failures occurred on the evening of August 6, approximately 6 hours before Banqiao failed. Small dams near Kaishan and Miang overtopped and breached, releasing their stored water downstream. This water added to the inflow arriving at Banqiao from direct runoff. The cascade effect was beginning. Each dam failure upstream sent a surge of water downstream, increasing inflow to the next dam in the sequence. By the time Banqiao failed, approximately 30 smaller dams had already failed. After Banqiao failed, the surge of water from the breach propagated downstream and overwhelmed the Shimontan Dam, a smaller structure located approximately 20 kilometers downstream of Banqiao. Shimontan failed within 2 hours of the Banqiao breach. Over the following 24 hours, a total of 62 dams in the basin failed in a cascading sequence. The divergence between what the system's indicators suggested and what the physical reality was can be summarized as follows. The water level gauges reported precise measurements of reservoir elevation, providing operators with accurate information about one variable. However, this single variable was insufficient to assess the state of the system. The operators did not know the inflow rate, did not know the actual discharge capacity of the obstructed spillway, did not know the rate at which the reservoir would fill, and did not know whether the embankment could withstand overtopping even briefly. The indicators provided an illusion of knowledge. The gauges worked perfectly. They reported the water level accurately every minute, but they did not report the information that mattered, which was whether the current discharge capacity was adequate to prevent overtopping given the current inflow. That question required integrating information from multiple sources, performing calculations, and making judgments under uncertainty. The system did not provide operators with tools or training to perform this integration. The decision forked the moment at which operators faced a choice between competing interpretations of the situation occurred around 8 p.m. on August 6, when the water level exceeded the normal maximum operating level. At that moment, operators could have interpreted the situation as, "We have opened all the gates, the spillway is discharging, the situation is under control, and the water level will stabilize," or they could have interpreted it as, "The water level is still rising despite all gates being open, which means inflow exceeds discharge, and overtopping is inevitable unless something changes." The first interpretation was consistent with their training, and with the assumption that the spillway, when fully open, would be adequate. The second interpretation required recognizing that the design assumptions had failed. The operators chose the first interpretation, not because they were incompetent, but because the system was designed to lead them to that interpretation. The physical processes that transformed the Banqiao Dam from an intact structure into a catastrophic breach can be understood only through detailed examination of the forces acting on the embankment, the material properties of the dam and its foundation, the hydraulic conditions during overtopping, and the feedback mechanisms that accelerated failure once erosion began. This chapter reconstructs the failure chain step by step, identifying each link in the causal sequence and explaining why the chain, once initiated, could not be interrupted. The analysis draws on post-failure investigations, breach geometry measurements, hydrological reconstructions of the flood wave, and engineering principles governing embankment erosion and mass balance. The initiating condition for breach formation was the sustained overtopping that began at approximately 1:30 a.m. on August 7, 1975. At this moment, the water level in the reservoir stood at 110 meters above sea level, equal to the original design crest elevation. The improvised reinforcement that had been added to the crest during the preceding hours had raised the effective crest elevation to approximately 110.5 meters in some sections, but this reinforcement consisted of uncompacted earth and sandbags placed hastily under emergency conditions. When water began to flow over this material, the erosive force of the flow immediately began to remove it. The critical hydraulic parameter governing erosion was the unit discharge, the flow rate per unit width of the crest. At the initial moment of overtopping, with the water level approximately 0.1 meters above the reinforced crest in the lowest section, the unit discharge was approximately 0.15 cubic meters per second per meter of width. This value, while modest compared to design spillway discharges, was sufficient to mobilize the uncompacted soil particles in the reinforcement. The erosion process proceeded in two phases: removal of the improvised reinforcement and erosion of the original embankment material. The first phase occurred rapidly. Within approximately 15 minutes of initial overtopping, the reinforcement had been completely washed away along a section of the crest approximately 10 meters wide. This removal exposed the original crest surface, which consisted of compacted clay and soil that had been placed during the dam's construction and modification. The original material had significantly greater resistance to erosion than the improvised reinforcement, but it was not designed to withstand prolonged exposure to flowing water. Earth embankment dams are designed on the principle that water will be retained within the reservoir and discharged through controlled outlet spillways and bottom outlets, and that the embankment surface will not be subjected to high-velocity flow. When this principle is violated, the embankment becomes vulnerable. The erosion of the original embankment material began at approximately 1:45 a.m. The mechanism was hydraulic scour. Flowing water exerted shear stress on the surface of the downstream slope, and when this shear stress exceeded the critical shear stress for the material, particles were detached and transported away by the flow. The critical shear stress for compacted clay typically ranges from 2 to 6 pascals, depending on the clay's plasticity, moisture content, and degree of compaction. The shear stress exerted by overtopping flow can be estimated using the relation tau equal to rho GRS, where tau is shear stress, rho is water density, 1,000 kilograms per cubic meter, g is gravitational acceleration, 9.8 meters per second squared, r is hydraulic radius, approximately equal to flow depth for wide, shallow flow, and s is the slope of the energy grade line, approximately equal to the bed slope for uniform flow. For the Banqiao embankment, the downstream slope was approximately 1:3, vertical to horizontal, corresponding to a slope s of approximately 0.33. With an initial overtopping depth of 0.1 meters, the hydraulic radius r was approximately 0.1 meters, yielding a shear stress of approximately 323 pascals, more than 50 times the critical shear stress for clay. This enormous excess of applied stress over resistance meant that erosion would proceed rapidly. As particles were detached from the surface, they were transported downstream by the flow, exposing the underlying material to the same erosive forces. The erosion front migrated vertically downward into the embankment and horizontally upstream toward the reservoir. The vertical migration created a head cut, a steep, nearly vertical scarp in the embankment material. Head cuts are characteristic features of embankment erosion. They form because erosion is concentrated at the base of the scarp, where flow velocity and turbulence are highest. As material at the base is removed, the material above loses support and collapses into the flow, either as individual particles or as larger blocks depending on the cohesion of the material. The collapsed material is then transported away, and the process repeats. The rate of head cut migration depends on the erosion resistance of the material and on the hydraulic conditions. For the Banqiao embankment, post-failure analysis estimated that the head cut migrated upstream at an average rate of approximately 5 meters per hour during the initial phase of breach development. When the head cut reached the crest of the dam at approximately 2 a.m., the breach process entered a phase of rapid acceleration. The arrival of the head cut at the crest effectively lowered the crest elevation in the breach zone, because material at the crest had been removed down to the level of the head cut base. This lowering increased the depth of water flowing over the breach, which increased the unit discharge, which increased the shear stress, which increased the erosion rate. The feedback loop was positive and self-reinforcing. Erosion caused deeper flow. Deeper flow caused more erosion. The breach depth increased at an accelerating rate. Within 30 minutes of the head cut reaching the crest, the breach had cut down approximately 3 meters below the original crest elevation, and the unit discharge had increased to approximately 15 cubic meters per second per meter of width, a 100-fold increase from the initial overtopping condition. Simultaneously with the vertical deepening of the breach, lateral widening was occurring. The lateral widening was driven by erosion of the breach sidewalls. As water flowed through the breach, it exerted forces on the sidewalls in addition to the bed. The sidewalls, initially vertical or near vertical, were unstable under these forces. The embankment material on the sides of the breach did not have sufficient shear strength to stand at a vertical angle, while submerged and subjected to flowing water. Blocks of material on the sidewalls collapsed into the breach channel, narrowing the channel temporarily and increasing the flow velocity through the constricted section, which then eroded the collapsed material and widened the breach again. The lateral widening rate was slower than the vertical deepening rate, because lateral erosion required not only detachment of particles, but also mass failure of blocks of material. Post-failure surveys indicated that the breach widened at an average rate of approximately 10 meters per hour during the peak phase of breach development, reaching a maximum width of approximately 372 meters. The geometry of the breach can be described by three parameters: depth, top width, and average width. The depth at the deepest point was approximately 29.5 meters, measured from the original crest elevation down to the base of the breach. This depth extended through the full height of the embankment and into the foundation material. The top width, the width of the breach measured at the original crest elevation, was approximately 372 meters. The average width, calculated as the width at mid-depth, was approximately 291 meters. These dimensions indicate that the breach was not a simple rectangular channel, but a trapezoidal cross-section with sloping sides. The side slopes of the breach stabilized at an angle determined by the angle of repose of the saturated embankment material, approximately 1:2 to 1:2.5. The discharge through the breach can be estimated using hydraulic principles. The breach acted as a broad-crested weir, with flow controlled by critical depth conditions at the crest of the breach. The discharge over a broad-crested weir is given by Q equal to CLH 3/2, where Q is discharge, C is a discharge coefficient, approximately 1.7 for broad-crested weirs, L is the effective length of the weir crest, the breach width, and H is the head above the weir crest. At the peak of the breach discharge, the water level in the reservoir was still approximately 108 to 109 meters, and the breach had cut down to approximately 80 to 81 meters, giving a head H of approximately 28 meters. With a breach width L of 372 meters, the peak discharge was Q equal to 1.7x 372x, 28, 3/2, approximately equal to 78,100 cubic meters per second. This calculated value matches the observed peak discharge estimated from downstream flood wave arrival times and inundation extent. The duration of high discharge through the breach was determined by the rate at which the reservoir drained. The reservoir at the moment of initial overtopping contained approximately 607.5 million cubic meters of water. During the breach formation and expansion phase, inflow to the reservoir from the upstream catchment continued at a rate of approximately 1,500 cubic meters per second, adding approximately 100 million cubic meters over the 5-hour breach period. The total volume released through the breach was therefore approximately 700 million cubic meters. With a peak discharge of 78,100 cubic meters per second, the reservoir would drain in approximately 2.5 hours if the discharge remained constant. However, the discharge was not constant. It decreased as the reservoir water level dropped and the head over the breach decreased. Integrating the discharge over time, accounting for the decreasing head, yields a total breach duration of approximately 5.5 hours. From initial overtopping at 1:30 a.m. to effective cessation of significant discharge through the breach at approximately 7 a.m. The mass balance during the breach process can be reconstructed by comparing inflow, spillway discharge, and breach discharge. At the moment of initial overtopping, inflow to the reservoir was approximately 1,500 to 2,000 cubic meters per second, and spillway discharge was approximately 600 cubic meters per second, yielding a net inflow of 900 to 1,400 cubic meters per second. This net inflow was increasing the reservoir volume at a rate of approximately 3.2 to 5 million cubic meters per hour. After the breach began to discharge significant volumes, approximately 2:30 am, the discharge through the breach exceeded both the inflow and the spillway discharge combined, resulting in a net outflow and a decrease in reservoir volume. The reservoir volume decreased at a rate of approximately 100 to 150 million cubic meters per hour during the peak phase of breach discharge, dropping the water level at a rate of approximately 2 to 3 meters per hour. The physics that invalidated operator interpretation can be summarized through the concept of two-phase flow and the limitations of water level as a diagnostic variable. Operators at Banqiao Dam were trained to use water level as the primary indicator of reservoir status. The mental model was straightforward. If water level is rising, inflow exceeds discharge. If water level is stable, inflow equals discharge. If water level is falling, discharge exceeds inflow. This model is correct under the assumption that the relationship between water level and volume is fixed, and that inflow and discharge can be controlled or predicted. However, the model breaks down under extreme conditions where inflow cannot be measured directly, discharge capacity is unknown due to obstruction, and the rate of rise is so rapid that operators cannot calculate whether stabilization is achievable. The water level gauge at Banqiao provided accurate readings of elevation, but elevation alone does not indicate whether the system is approaching a critical threshold beyond which recovery is impossible. The point of no return can be defined as the moment at which overtopping became inevitable regardless of operator action. This moment occurred when the net inflow to the reservoir exceeded the maximum possible discharge capacity under any feasible gate configuration, and when the remaining freeboard was insufficient to accommodate the volume of water that would arrive before inflow decreased. For Banqiao Dam, this point of no return can be calculated retrospectively. At 8 p.m. on August 6, the water level was 108.3 meters, freeboard was 2.2 meters, and net inflow was approximately 900 to 1,400 cubic meters per second. The reservoir surface area at this elevation was approximately 63 square kilometers or 63 million square meters. A net inflow of 1,000 cubic meters per second into a reservoir of this surface area raises the water level at a rate of 1,000 cubic meter per second, 63 x 10⁶ square meters, equal to 0.000016 meters per second, or approximately 0.06 meters per hour. However, as the water level rises, the surface area increases, reducing the rate of rise slightly. Integrating over the remaining freeboard of 2.2 meters, with a net inflow of 1,000 cubic meters per second and accounting for increasing surface area, the time to overtopping was approximately 40 hours. But this calculation assumes constant net inflow. The actual net inflow increased as the storm intensified, accelerating the time to overtopping. A more realistic calculation, using the observed rate of rise between 8 p.m. on August 6 and 1 a.m. on August 7, approximately 1.7 meters in 5 hours, or 0.34 meters per hour, indicates that the time to overtopping from the 8 p.m. condition was approximately 6.5 hours, putting the expected overtopping time at approximately 2:30 a.m. on August 7 close to the observed time. This calculation suggests that by 8 p.m. on August 6, overtopping was already inevitable unless inflow decreased or discharge increased. Inflow did not decrease, the storm continued. Discharge could not be increased because the gates were already open as far as they could be opened given the obstructions. Therefore, the point of no return had been reached by 8 p.m. on August 6, approximately 5.5 hours before overtopping actually began. After this point, no action available to the operators could have prevented overtopping. The question of whether earlier action could have prevented failure requires examining the timeline more closely. If the gates had been fully opened 24 hours earlier at 8 p.m. on August 5, when the water level was 105.5 meters and freeboard was 5 meters, would the outcome have been different? At that time, inflow was lower, approximately 500 cubic meters per second, and if all gates had been fully opened, achieving a discharge of 800 cubic meters per second, the reservoir would have been in a net discharge condition, and the water level would have stabilized or even decreased. However, this action would have required operators to anticipate that an extreme flood was developing and to violate normal operating procedures, which called for maintaining high reservoir levels. The decision to open gates fully would have required authorization from the regional bureau, and such authorization would have required the bureau to have accurate forecasts of the storm's behavior and rainfall magnitude. The meteorological forecasts available on August 5 did not predict the extreme rainfall that would occur over the following 3 days. Typhoon Nina had made landfall and was expected to weaken. The forecast called for heavy rainfall, but not for record-breaking rainfall exceeding design values by a factor of 2.5. Without this forecast, the decision to preemptively lower the reservoir would have appeared unjustified, particularly given the emphasis on maintaining water for irrigation. Even if the gates had been opened fully on August 5th, the outcome might still have been failure, because the extreme inflow that developed by August 6 would have exceeded even the full spillway discharge capacity. The inflow of 1,500 to 2,000 cubic meters per second exceeded the designed spillway discharge of 800 cubic meters per second, or the obstructed actual discharge of 600 cubic meters per second by a factor of 2 to 3. Unless the reservoir had been completely empty at the start of the storm, an operationally and politically unacceptable condition, the reservoir would have filled eventually. The only difference would have been the timing. Starting from a lower initial level would have bought additional time before overtopping, but it would not have prevented overtopping unless the storm ended before the reservoir filled. The storm did not end. It continued for more than 72 hours. Therefore, the fundamental problem was not operator decision-making or procedural failures. It was the mismatch between the spillway discharge capacity and the extreme inflow. The design assumption that a 1,000-year flood would not exceed 1,742 cubic meters per second had been invalidated by the storm. Once that assumption failed, the dam was destined to fail unless the storm ceased. The feedback loop between actions based on a false plant picture and worsening of the plant picture can be traced through the operator's decision sequence. At each stage, operators believed they were taking appropriate action. They opened gates progressively, reported conditions when communication was available, attempted to reinforce the crest when overtopping appeared imminent, and evacuated when failure became obvious. Each action was rational given their understanding of the situation. However, their understanding was based on the assumption that the spillway, when opened, would provide adequate discharge capacity. This assumption was false due to obstruction and due to the extreme inflow. Because operators could not see the obstruction or measure the inflow, they could not recognize that the assumption was false. Their actions opening gates and waiting for the reservoir to stabilize were predicated on a model of the system that no longer corresponded to reality. The system's information architecture did not provide them with the data needed to recognize the discrepancy. The water level gauge told them the reservoir was rising, but it did not tell them why the gates were ineffective or what inflow rate would be required for stabilization. Without this diagnostic information, operators continued to trust that their actions were correct. Even as the situation deteriorated, the erosion of the embankment foundation also contributed to the breach process. Beneath the clay embankment, the foundation consisted of natural soil and weathered rock. When the breach cut through the full height of the embankment, the base of the breach reached the foundation material. The flowing water exerted erosive forces on the foundation, though at a lower rate than on the embankment material, because the foundation was more resistant. Nevertheless, some erosion of the foundation occurred, deepening the breach by an additional 1 to 2 meters below the base of the embankment. This deepening increased the discharge slightly and allowed more complete drainage of the reservoir. Post-failure inspection of the breach showed that the foundation erosion was limited to the central portion of the breach, where flow velocities were highest, and that the outer portions of the breach base remained close to the original foundation elevation. The hydrogen generation, gas accumulation, and secondary crises that can occur in nuclear reactor accidents did not have direct analogs in the Banqiao Dam failure. However, there was a secondary crisis in the form of the cascade failure of downstream dams. The flood wave released by the Banqiao breach propagated downstream at high velocity. The wave arrived at the Shimantan Dam, located 20 kilometers downstream, at approximately 3:30 a.m. on August 7th, less than 2 hours after the Banqiao breach began. At that time, Shimantan Dam was already at high water level due to the same storm that had affected Banqiao. The arrival of the Banqiao flood wave increased the inflow to Shimantan from an already high baseline of approximately 800 cubic meters per second to a peak inflow of approximately 30,000 cubic meters per second. This sudden increase overwhelmed Shimantan's spillway, which had a design capacity of approximately 500 cubic meters per second. Shimantan overtopped and breached within 30 minutes of the flood wave arrival. The breach of Chamontin released an additional 120 million cubic meters of water, which propagated further downstream and contributed to the failure of additional dams in the cascade. The physical evidence from the breach confirms the erosion mechanism described above. Surveys conducted in the weeks following the failure documented the breach geometry in detail. The breach was approximately 372 meters wide at the top, 291 meters wide on average, and 29.5 meters deep. The breach side slopes were approximately 1.2 to 1.2.5. The breach orientation was perpendicular to the dam axis. The material eroded from the breach was deposited downstream in a fan-shaped delta extending several hundred meters from the dam toe. The volume of material in this delta, estimated from survey measurements, was approximately 1.2 million cubic meters, consistent with the volume of embankment and foundation material removed from the breach zone. The breach base was irregular, with localized deeper zones where foundation erosion had been concentrated, and shallower zones where more resistant rock was exposed. The embankment material remaining on either side of the breach showed no evidence of internal erosion or piping prior to the breach formation, indicating that the failure was purely a result of overtopping erosion, not of internal seepage-related processes. The failure chain can be summarized. Extreme rainfall exceeded design assumptions by a factor of 2.5, producing inflows that exceeded spillway capacity by a factor of 2 to 3. Sedimentation reduced spillway discharge capacity below design values. Operators opened gates, but could not achieve sufficient discharge to prevent reservoir filling. Communication failure isolated operators and prevented coordination with higher authorities. The reservoir filled to the crest. Improvised reinforcements failed rapidly. Overtopping initiated erosion of the embankment. Erosion created a headcut that migrated to the crest. Crest lowering increased overtopping flow, accelerating erosion. The breach deepened and widened in a self-reinforcing feedback loop. The reservoir drained through the breach over 5 hours. The flood wave overwhelmed downstream dams, initiating a cascade failure. Each link in this chain was causally necessary. Remove any single link and the chain might have been interrupted. But the conditions that created each link were structural features of the system design assumptions, institutional priorities, operational procedures, instrumentation limitations, and these features were not easily changed. The failure was not an accident in the sense of an unpredictable event. It was the inevitable outcome of a system operating under conditions that violated its design assumptions. The period following the initiation of the Banqiao Dam breach on August 7, 1975, was characterized by a desperate attempt to stabilize a regional hydrological system that was disintegrating across multiple nodes simultaneously. The stabilization efforts were not limited to Banqiao itself. By the time the breach was fully developed, Banqiao was beyond saving, but extended to dozens of other dams in the basin, to emergency flood control measures downstream, and to improvised attempts to protect population centers from the advancing flood wave. These efforts were constrained by the same factors that had contributed to the failure: communication breakdowns, limited understanding of the evolving situation, inadequate resources, and the sheer magnitude of the forces involved. This chapter examines the stabilization attempts, the secondary crises that emerged as the flood propagated through the basin, and the reasons why the physical state of the system remained uncertain even after the most acute phase of the emergency had passed. At approximately 3 a.m. on August 7th, when the breach at Banqiao Dam had reached a width of approximately 50 meters and was discharging water at a rate exceeding 20,000 cubic meters per second, operators at the dam site recognized that the structure was lost. The immediate priority shifted from preventing the breach to warning downstream populations and attempting to mitigate the impact of the flood wave. However, the means to accomplish this were severely limited. The telephone lines connecting the dam to the Regional Water Resources Bureau and to downstream towns remained inoperative due to storm damage. The operators who had attempted to travel by bicycle to reach a functioning telephone had not yet returned. They would not arrive at the nearest operational communication point until approximately 4 a.m., by which time the breach was already well advanced. Radio communication equipment which might have provided a backup was not installed at the dam. The only means of warning available was physical travel by individuals attempting to reach villages in the flood path before the water arrived. Several operators and local residents who had been present at the dam during the breach formation departed on foot and by bicycle at approximately 3:30 a.m., traveling toward the towns of Sweeping and Dawancheng, located 15 and 25 kilometers downstream respectively. The flood wave, traveling at an average velocity of approximately 50 kilometers per hour on the open plain, would reach Sweeping within approximately 18 minutes of the messenger's departure and Dawancheng within approximately 30 minutes. The messengers had no possibility of arriving before the flood. Their travel speed on foot was approximately 5 kilometers per hour, and by bicycle perhaps 15 kilometers per hour, on roads that were already partially flooded and obstructed by debris. The messengers reached Sweeping at approximately 4:15 a.m., nearly 1 hour after the flood wave had already passed through the town. They reached Dawancheng at approximately 5 a.m., also after the flood had arrived. The warning effort, though undertaken with urgency and at personal risk, was ineffective due to the travel time differential. At the Regional Water Resources Bureau located in Jumadian Prefecture, the first confirmed information about the Banqiao breach arrived at approximately 4:30 a.m. on August 7th, when the bicycle messenger who had departed from the dam at 9 p.m. on August 6 finally reached a functioning telephone and placed a call to the Bureau. The message conveyed was fragmentary. The dam had been overtopping, communication had been lost, and the situation was critical. The Bureau officials, receiving this information, immediately attempted to establish contact with other dams in the basin to assess the broader situation and to coordinate emergency responses. They discovered that communication with most dams was disrupted. Telephone lines throughout the region had been damaged by the storm. The officials were operating with incomplete information, unable to determine which dams had failed, which were at risk of imminent failure, and what the status of the flood wave was as it propagated through the basin. The Bureau's response, constrained by these informational limitations, focused on 3 priorities: attempting to stabilize dams that were still intact but at risk, coordinating evacuations in downstream areas, and mobilizing military and civil defense resources for rescue and relief operations. The first priority required identifying which dams were most at risk. Based on the limited reports available, officials identified approximately 15 major dams that were believed to be at or near capacity and at risk of overtopping. For each of these dams, the Bureau issued emergency authorizations for operators to take extraordinary measures, including preemptive breaching of sections of embankments in controlled locations to release water laterally rather than allowing uncontrolled overtopping over the crest. The rationale for controlled breaching was that a lateral breach, if executed in a planned location with a gradual initiation, would release water at a lower rate and with less erosive force than an overtopping breach, and would allow some degree of control over the direction and timing of the release. However, the execution of controlled breaching proved to be difficult. The procedure required access to explosives or heavy equipment to excavate sections of the embankment, neither of which was readily available at most dam sites during the storm. Additionally, the decision to breach a dam preemptively was politically and psychologically difficult. Dam operators and local officials were trained to preserve dams, not to destroy them. The decision to breach implied accepting the loss of the structure and the flooding of downstream areas that the dam had been built to protect. In several cases, operators hesitated or refused to implement the breaching orders, hoping that the storm would subside before overtopping occurred. In other cases, operators attempted to breach but lacked the tools or expertise to do so effectively. In a few cases, controlled breaching was successfully executed and did reduce the severity of downstream flooding compared to what would have occurred with uncontrolled overtopping. But the overall success rate of the controlled breaching strategy was low. The second priority, coordinating evacuations, was hampered by the communication failures and by the limited advance warning time. In theory, an evacuation requires notification of the population at risk, designation of safe zones to which people should move, provision of transportation for those unable to move independently, and sufficient lead time for the movement to be completed before the hazard arrives. In practice, none of these elements were fully achievable during the night of August 7th. The population in the areas downstream of Banqiao and other failing dams numbered in the hundreds of thousands. distributed across hundreds of small villages and several towns. Notification would have required a functioning communication network reaching to the village level, which did not exist. Designated safe zones would have required prior hazard mapping to identify areas above the flood inundation elevation, which had not been conducted. Transportation was limited to whatever vehicles and draft animals were locally available, and many roads were already impassable. Lead time was measured in minutes, not hours. The Jumadian prefecture government, upon receiving confirmation of the dam failures, issued a general evacuation order at approximately 5 a.m. on August 7 for all areas within the predicted flood zone. The order was transmitted via radio broadcast and via messengers sent to county and township governments. However, the radio broadcast reached only those who had access to radios and who were listening at that hour, a small fraction of the population. The messengers, traveling by vehicle where roads were passable and on foot where they were not, required hours to reach outlying areas. By the time the evacuation order reached many villages, the flood had already arrived. In villages where the order was received in time, the response was often chaotic. Residents, awakened in the middle of the night and told to evacuate immediately, attempted to gather belongings, locate family members, and move to higher ground. In the darkness and heavy rain, with limited knowledge of the local topography and no guidance on where to go, many people made decisions that put them at greater risk rather than less. One documented case illustrates the difficulties. In the town of Shahidian, located on the Ru River approximately 10 kilometers downstream of Banqiao Dam, an evacuation order was received at approximately 4 a.m. on August 7 via a messenger who arrived by motorcycle. The town's Communist Party secretary convened an emergency meeting of local officials and decided to evacuate the population to a nearby area of higher ground approximately 3 kilometers to the north. However, the higher ground was accessible only by a single road, which was already congested with people attempting to flee other areas. The evacuation became a bottleneck. By the time the flood wave arrived at approximately 4:30 a.m., only a portion of Shahidian's population of approximately 6,000 had successfully reached the higher ground. The remainder were trapped in the town or on the road. The flood wave, approximately 6 meters high when it reached Shahidian, swept through the town at high velocity. Survivors reported that entire buildings were demolished within seconds, that vehicles and livestock were carried away, and that people who had been attempting to evacuate on the road were overtaken by the water. Of Shahidian's 6,000 residents, approximately 827 perished in the flood. The town itself was largely destroyed. The third priority, mobilizing rescue and relief resources, faced the challenge of operating in conditions where transportation was severely disrupted. The flood had inundated roads, destroyed bridges, and isolated many affected areas. Military units from the People's Liberation Army were mobilized on the morning of August 7, but they required time to reach the affected areas, and upon arrival, found that access to many villages was impossible by ground. Helicopters, which might have provided aerial access, were extremely limited in number and were grounded during the height of the storm due to poor visibility and high winds. The first helicopter flights to survey the affected areas did not occur until the afternoon of August 8, more than 30 hours after the Banqiao breach. These flights provided the first comprehensive visual documentation of the extent of the disaster. Pilots reported that vast areas of the plain were underwater, that entire villages had disappeared, and that survivors were visible stranded on rooftops, on sections of embankment, and in trees. The rescue operations that followed were constrained by the physical environment. The floodwaters, initially moving at high velocity, gradually slowed as the flood wave dispersed over the plain, but the water remained deep in many areas, 2 to 4 meters deep for several days. Rescue teams using boats were able to reach some stranded survivors, but the number of boats available was insufficient relative to the number of people in need. Many survivors spent days without food or clean water, surrounded by contaminated floodwater. The risk of disease outbreaks, particularly waterborne diseases such as cholera, dysentery, and typhoid, was high. Medical supplies and personnel were mobilized, but distribution was slow due to access constraints. The secondary crises that emerged in the aftermath of the flood were multifaceted. The immediate crisis was the loss of life. The official death toll from the Banqiao and Shimantan Dam failures and the subsequent cascade failures was initially reported as approximately 26,000, though this figure was later revised upward. A 1995 report by Human Rights Watch cited estimates from the Chinese People's Political Consultative Conference suggesting that the true death toll, including deaths from subsequent famine and epidemics, was approximately 230,000. The discrepancy between these figures reflects the difficulty of accounting for deaths that occurred not in the immediate flood, but in the weeks and months that followed, due to starvation, disease, and exposure. The secondary crisis of disease was severe. The floodwaters contaminated wells, water supplies, and agricultural land. The bodies of humans and livestock decomposing in the floodwaters created conditions conducive to the spread of infectious disease. By August 18, 1975, medical reports documented outbreaks of dysentery, malaria, and other diseases in the affected areas. The medical response included the airlift of medical teams and supplies, mass inoculation campaigns, and the establishment of temporary field hospitals. However, these efforts were reactive and could not fully prevent the disease outbreaks. The total number of deaths attributable to disease in the flood's aftermath is uncertain, but likely numbered in the thousands. The tertiary crisis was economic and agricultural. The flood inundated approximately 1.1 million hectares of agricultural land, much of it during the critical late summer growing season. Crops that had been nearing harvest were destroyed. The flood deposited layers of sediment over fields, in some cases rendering the land temporarily unsuitable for cultivation. Livestock losses were extensive. Hundreds of thousands of pigs, cattle, and draft animals perished in the flood or died subsequently due to lack of feed and shelter. The economic losses, calculated in 1,975 yuan, exceeded 1 billion, a staggering sum for a region that was already economically underdeveloped. The loss of the harvest contributed to food shortages in the subsequent months, exacerbating the mortality from disease. The challenge of assessing the internal state of surviving dams in the basin was significant. Many dams had experienced high water levels and overtopping or near overtopping during the storm. Even dams that had not failed might have sustained internal damage, erosion of the embankment, development of seepage paths, settlement or cracking that compromised their structural integrity. However, inspecting these dams to assess their condition was difficult during the immediate post-storm period. Water levels remained high, access was limited, and inspection resources were prioritized for rescue and relief rather than for structural assessment. As a result, the condition of many dams remained uncertain for days or weeks after the storm. There was concern that additional failures could occur as delayed effects of the extreme loading manifested. Inspection teams were eventually deployed to conduct visual assessments of dams throughout the basin. These teams identified numerous dams with visible signs of distress, cracks in the embankment crest, seepage on the downstream slope, settlement of the crest, and erosion of spillway structures. In several cases, dams that had not failed during the storm were found to be in precarious condition and were deliberately breached or drawn down to reduce the risk of uncontrolled failure. The inspection process revealed the extent to which the storm had stressed the entire dam inventory in the region, not just the dams that had failed. The question of whether the situation was stable even after the acute flood phase had passed remained open for weeks. The floodwaters, once they had inundated the plain, did not drain rapidly. The region's topography was flat, drainage was impeded by sediment and debris, and the existing drainage infrastructure, canals, ditches, and rivers, had been damaged or blocked by the flood. In some areas, standing water remained for more than a month. The prolonged inundation created ongoing risks. Structures that had survived the initial flood wave weakened and collapsed days later due to prolonged submersion. Survivors stranded in flooded areas faced starvation and disease, and agricultural land remained unproductive. The transition from acute emergency to recovery was gradual and uneven. The decision-making during the stabilization phase shifted from reliance on procedures to reliance on expert judgment under conditions of extreme uncertainty. Officials at the regional and provincial levels were making decisions about which dams to try to save, which to abandon, where to allocate limited rescue resources, and how to manage the competing demands of immediate rescue versus longer-term recovery. These decisions were made without complete information, without clear precedents, and under intense time pressure. The decision-making process was necessarily ad hoc. There were no established frameworks for managing a disaster of this magnitude. Officials drew on their experience, their understanding of the physical and social landscape, and their judgment about priorities, but they operated in an environment where the costs of every decision were measured in lives. One example of expert judgment under uncertainty was the decision to dynamite sections of the embankments of several downstream dams that were still intact but at risk of being overwhelmed by the flood wave from upstream failures. The rationale was that by breaching these dams in a controlled manner, the flood wave could be attenuated and dispersed over a wider area, reducing peak flood depths in critical locations downstream. The decision required calculating the expected arrival time of the flood wave, estimating the volume of water that would arrive, assessing the capacity of the dams to withstand this volume, and determining the optimal locations and timing for the controlled breaches. These calculations were performed with limited data and required assumptions about flood wave propagation in a complex, partially urban environment. In some cases, the controlled breaches were executed successfully and did reduce downstream flood impacts. In other cases, the breaches were executed too late, or in locations that did not achieve the intended effect. The uncertainty about what had actually happened inside the Banqiao Dam embankment in the moments before and during the breach could not be resolved immediately. The embankment had been destroyed, the breach had removed the evidence that might have allowed forensic reconstruction of the internal processes. Questions remained: had internal erosion or piping contributed to the failure, or was it purely an overtopping failure? Had the foundation been undermined before the breach reached it, or had foundation erosion occurred only after the embankment was removed? Had there been differential settlement or cracking in the embankment that predisposed it to rapid erosion? These questions could only be answered through detailed post-failure investigation, including examination of the remaining embankment sections, drilling and sampling to assess foundation conditions, and analysis of the breach geometry and erosion patterns. The stabilization attempts ultimately succeeded in preventing the complete collapse of the regional water management system, but they did not prevent massive loss of life and destruction. The flood wave was eventually dispersed and absorbed by the natural and artificial drainage features of the plain. Water levels gradually receded. By late August 1975, the acute emergency phase had ended, and the focus shifted to recovery, restoring transportation infrastructure, repairing surviving dams, providing shelter and food for displaced populations, preventing disease outbreaks, and beginning the process of agricultural rehabilitation. However, the memory of the disaster and the recognition that the dam system had failed catastrophically under conditions that, while extreme, were not impossible, prompted a fundamental reassessment of dam design, operation, and safety oversight in China. The physical evidence available in the immediate aftermath consisted of the breach itself, the downstream flood damage, survivor accounts, and limited photographic documentation. The breach at Banqiao was surveyed within days of the failure, providing the geometric data width, depth, side slopes that have been used in subsequent analyses. The flood damage downstream was documented through aerial surveys and ground reconnaissance, allowing estimation of inundation extent, flow velocities, and destruction patterns. Survivor accounts provided information about the timing of events, the behavior of the flood wave, and the effectiveness, or lack thereof, of warnings and evacuations. Photographic documentation was limited due to the conditions during the storm and the restrictions on information dissemination that were in place in China at the time, but some photographs taken in the days after the flood have been preserved and provide visual evidence of the scale of destruction. The lessons that could be derived from the stabilization phase were clear. Communication systems must be resilient under the conditions in which they will be needed most. Evacuation plans require advanced preparation, designated safe zones, and realistic estimates of required lead time. Controlled breaching of dams is a viable emergency measure, but requires pre-positioned equipment and trained personnel, and the physical state of a dam after an extreme loading event cannot be assumed to be stable without thorough inspection. These lessons, however, were learned at an enormous cost.